Good morning, everybody, and thanks for tuning in to another version of our EMO Hanover 2023 webcast, which we are producing together with WGP, the German Academy of the Production Sciences. You know it as Let's Talk Science, and we have a very interesting topic for you today. We are going to deal with the topic of classic sheet metal forming, becoming more ecological and economical. So all of you know that in sheet metal forming, we use a lot of lubrication, which has in terms of waste and pollution, and economical situation in terms of additive substances that we might want to get rid during the process. And our two guests we have today are going to talk to you about how we can reduce or get rid of lubrication in the deep drawing process. This means that we can both save the environment and reduce cost. I think a very interesting topic here. Our guests today come from the beautiful city of Erlangen and are representing the Institute of Manufacturing Technology of the Friedrich Alexander University of Erlangen-Nürnberg. And I welcome Professor Hinak Hagener and Mr. Stefan Schirdewan, who are in that regard dealing in the research group for sheet metal forming with all the aspects how to improve sheet metal forming, which you know is a very important technology, especially in the car manufacturing industry. So I'm eager to hear what they can tell us. Again, thanks for tuning in. If you have any questions, nothing easier than that. You should see in your GoToWebinar panel a button which says questions, or German Fragen. So if you put down your questions there, even as they pop up during the presentation, please feel free to do so. And after the presentation is finished, we'll have a short round in discussing the questions with our two guests. And if the questions might be too lengthy to answer here, we make sure that you get some answer afterwards. But now, Professor Hagener, Mr. Schirdewan, the floor is yours, and all the best, and talk to you later.
Thank you very much for the kind introduction, Dr. Broos, and I welcome all the persons in the audience. Thank you very much for turning in so early. The topic of this presentation is on the slide. It is sustainable and resource efficient sheet metal forming, generation of economic and ecological advantages by realizing lubricant-free deep drawing, which is a very lengthy title. The agenda of what we are going to present is at the bottom left. But basically, I would like to draw your attention to the two figures or images on the slide, which very nicely sums up what we are going to deal with. On the left-hand side, we see a cup, something like a cup, deep drawn, and we see like it is done everywhere in industry today. We are using lubrication here and a lubricant, and we receive a acceptable geometry with a sheet thickness that is also in the range that we want to achieve. On the right-hand side, we remove the lubricant, and what we see there is that sheet thickness is reduced significantly, might be below some certain thresholds. So this is basically what we are going to look at. Can we reach the same geometry with sufficient sheet thicknesses without a lubricant in order to achieve a more green process? If we turn to the next slide, we can see the motivation, which is not really surprising and more or less what is known by most people, I guess. We do have to deal with an increasing environmental awareness in the general public, which means everybody is asking, is it green or not? Which is also resulting in the aspect that there is a demand for green forming technologies. Furthermore, harmful substances or products whose production are involving harmful substances should be avoided, which is also a consequence of these environmental awareness. And somehow this has to be also brought together with the idea that still after all, production technology in the end for industry is about making money. So it would be nice if this could be combined with the reduction of process and system costs as well, in order to achieve where we are. And one of the big levers that can be used here is indeed friction, because friction is a major obstacle in forming technologies. We have it everywhere, and it needs to be reduced and overcome usually, or at least adjusted in a most favorable way. And usually when talking about friction, the first idea that everybody has is lubrication and lubricants. So that is the idea where we can try to move conventional production technologies towards a more green forming version of the process. And to give you an idea about what lubrication and friction is about, there is a short 50-second video that is coming next, that is directly coming from industry. I will be muted during the video, so please enjoy.
The strength and versatility of steel makes it the material of choice for so many things that make our life so comfortable. From cars we drive, to the appliances in our kitchen, from the buildings we work and live in, to many gadgets, they are all made of steel. To make steel into products, sheets of steel are cut in blanks and formed in products through various forming processes. Most commonly through a process called deep drawing. Europe has a long tradition when it comes to making quality steel products. In the manufacturing industry, perhaps more than in any other sector, time is money. Even a small increase in production speed can result in €1 million a year savings for a single company and billions at sector level. But going faster also has a downside. The faster a product is made, the tools forming the product heat up due to plastic energy released by the deformed metallic parts. The higher the temperature, the higher the frictional forces, which increase until a defect occurs in the material. At this point, the production must be stopped. At the level of a large company such as Opel, reducing downtime means millions € savings annually.
So what we saw in the video was one of the reasons why friction is increasing and a problem during forming processes. There are others, and the current solution to this is lubrication. And what we see here is that we do need lubrication in today's forming processes. However, lubrication is counteracting the aforementioned current global trends, because usually if we take a look at the benefits first, if we use lubricants, we do need lower forces during the forming processes, which is positive because this also means we need less energy. We do have a longer tool life usually, as with the lubrication we do reduce friction, and this means if we use a tool for a longer time, not only does it make more money, also we do not need to make another tool, and so we do not have to do another process in tool making, which is also polluting the environment somehow. One aspect of lubrication is that very often the lubricant is also used to prevent oxidation of the metal specimen, which avoids removing the oxide layer afterwards, and so it's also positive. And some forming processes, or most actually used forming processes today, are only possible with lubrication. So these are the good sides. The downside is that most of the lubricants are at some point made from oil, which is not very good in agreement with environmental awareness and reduction of pollution. Furthermore, very many lubricants are toxic, so it directly counteracts the idea of avoiding contact with harmful substances. And then we can say that if we look at the bottom right of the slide, you can see this process chain where we have a lubrication step, a forming step, and then a cleaning and drying step, and afterwards the process chain goes on. So there is a potential, if we don't have lubricants, that the process chain gets shorter, which is always a benefit. And after all, lubricants do cost money. They don't come for free. So there are ideas that could make it a good idea to remove lubricants, and it might furthermore be a signal to other process product manufacturing sectors. If we can avoid these substances here, maybe we can avoid them somewhere else. So those are the approaches and ideas. And if we look at the next slide, we can see there the conventional sheet metal forming chain that I already introduced. And if we remove the lubricant, then we can say we have directly the forming, joining, coating. So 2 steps removed, which of course says, okay, this is good. And the potentials on the bottom left of the slide I have already introduced. We might get more environmentally sustainable. We might have a greener technology, and we could even reduce production costs by removing steps from the process chain. All this is very nice. However, there is nothing like a free lunch, as you always know. There are some challenges that have to be overcome, and that is the increased friction. Increased friction leads to increased wear, both adhesive and abrasive. And in the process chain we're looking here, it's mostly the adhesive wear that is a problem. And it can also lead to a reduced part quality, which was shown on the very first slide, where the sheet thickness was reduced. You might also get some damages to the part or even a failing production process. All this results in the fact that you have to say, we have to overcome this somehow. And the research approach we followed in the projects that are behind this presentation is that we said, okay, looking, and I always like this approach, at our daily experience, there is sandpaper, and sandpaper exists in different grades, and the finer the grade is, the lower the friction is, and the lower is the abrasive wear. So the idea is there, this depends on the surface of the sandpaper. Can we somehow transfer this idea to the forming process and say, can we create a surface that minimizes friction and in consequence wear in forming processes? The idea was that we do not want to introduce any changes to the workpiece, because the workpiece basically is what the customer wants and demands. So changing the workpiece is not really, you will have to do work to sell the changed product afterwards. So better you don't change the product, somehow we change the tool. Furthermore, if we keep the forming process and the product basically the same, we don't need new machine tools, so we don't have such a big invest again. We can easily use the same machinery, result in the same product. We change the tools, which have to be changed every now and then anyways. So the idea is, what can we do to the tool? How can we modify the tool to reach the conditions we would like to have? And the idea there is, okay, we could use some coatings there, because if we think again of the sandpaper, it's also the surface and what we put on there, the paper underneath isn't changed so much. And to address this research question, how can we adjust the tool topography by using coating systems? We had a large research group consisting on the next slide of 10 institutes, 3 of them located in Erlangen. And what they tried to achieve within 6 years of research was to understand first, what happens in the process without lubricant? What is the interaction between tool and workpiece there? Because first you need to understand what happens, and after you understood, you can then try to derive measures, which is the second step, to improve these conditions and maintain product quality. And the third step then is to move this approach towards industrial application and see what is the tool life expectancy that we can derive from this, what can we get to for the real-world application outside of the laboratory. If we look at this at somewhat detail on the next overview slide, we can see there that we have these 3 steps I mentioned before. On the left, we see what do we want. We have the traditional approach with workpiece, lubricant, and tool. We have some friction coefficient there, and then we have the dry situation. And what we want to figure out here is what kind of friction coefficient would be acceptable, what do we need to reach, what is mandatory to have a process that is still capable of producing the kind of workpieces we would like to have. In the middle, we then look, okay, how can we get there? What is the approach regarding coatings and structuring of the coatings? I give as a brief idea, everybody has heard of the lotus effect. We don't have a totally flat surface there. We have a structured surface, yet the friction is so low that nothing is adhering to this surface. So can we somehow have a combination maybe with structure and coating technology to reduce the friction coefficient to a level that is acceptable? And after we achieve that, we will go on the very right-hand side towards the approach and use in a serious process and see what do we get there. Does our laboratory approach of coating and structuring stand a sufficient number of workpieces in reality? The ongoing presentation will focus on the middle and the left-hand side. The right-hand side is, I would say, work in progress and the future. And so the idea was on the next slide to use diamond-like coatings in this approach because those are known. They build amorphous films on top of the tool surface. They have a high hardness, they have high wear resistance, and they result in low friction coefficients. This sounds perfect. There's 2 processes that can be used to apply these coatings to the surface. The one is the pulsed laser deposition, which is, so to say, similar to an additive process. You have a laser and you have a material and you apply it to the surface. We result in extremely high hardness here, and we have a very good layer adhesion, which means the coating is not that easily removed from the original tool, and adhesion and abrasion resistance is very high. However, this process is slow and might have some limitations regarding the reachable geometry, because somehow you have to get there to apply the laser pulses. The second process with a very long name, plasma enhanced chemical vapor deposition, overcomes these obstacles and has the additional benefit of allowing for more variations that can be applied. However, although adhesion and abrasion resistance is also given, the layer adhesion is lower, still okay, but lower, and the hardness is not that high. On the next slide, there will be a short video introducing this process. And with that video, I will say thank you for your attendance, and Mr. Schirdewan will take over for the remainder of the presentation and show you some details that have been elaborated during these research projects.
Yeah, Henrik, thanks a lot for that nice introduction. Yeah, within this project, a deep drawing process of a rectangular cup, which can be seen in the upper right corner, has been used to investigate the process condition for a lubricant free forming. Yeah, at first to gain a basic knowledge or basic understanding and to identify the main influencing parameters, numerical simulations have been conducted. The forming process is modeled by using a FE software tool called Steiner. The rectangular cup, which can be seen in this upper right corner, has a cup width of around about 50 millimeters and a length about 90 meters. Yeah, and to reduce the computational time, it's normal that the symmetry of the workpiece is used because in all missing parts, the same results are expected. Yeah, for these FE models, different materials have been used. In this regard, DCO4 is steel material, as well as two aluminum alloys, AA51 and AA6014, has been used with a sheet thickness of 1 millimeter as workpiece material. At first, these materials are characterized at our institute in order to analyze the stress strain curves and the forming limit crust. Afterwards, these experimental data were integrated into the software tool to reveal a realistic forming behavior of the cups. In these lower pictures, you can find the forming limit crust for different materials and friction coefficients. When major and minor strains exceeded the forming limit curve, these are these black lines, which you can see here, and material failure in terms of crackings occurred. The results reveal that aluminum alloys, here AA5182 and AA6014, have a similar level, whereas DCO4 achieves a much higher formability level. This is no surprise for us since DCO4 has a higher tensile strength. Besides these material input parameters, the integration of different friction coefficients is necessary to analyze the different forming behavior. In this regard, different friction values, which you can see here in the blue colors, were set up for different material combinations in order to analyze the forming limit curves of the rectangular cup without material failure. The results reveal that DCO4 works for all friction coefficients set up to 0.2. However, aluminum will fail with friction coefficients above 0.3. The black lines are crossed, which you can see here, which show that material failure in terms of crackings are expected. It also can be seen that aluminum alloy AA5182 has an improved topological behavior compared to aluminum alloy AA61. So now the task for us was to generate a surface coating with friction coefficients under 0.3 in order to enable a failure-free forming without any lubricants. In the first step, to verify the reliability of the FE simulations and the feasibility of deep drawing processes, rectangular cups have been formed with and without lubrications. For this purpose, a deep drawing tool, which can be seen here in the upper left corner, was used, which mainly consists of a die, a blank coder, a punch, and load cells in order to measure the maximum punch forces and blank holder forces. Afterwards, the sheet thickness distribution of several cups was analyzed by using a topometric sensor to gain a deeper knowledge regarding the quality of the stamped components. By using lubricated sheets, failure-free forming of all tested materials was possible. The highest sheet thickness reduction was always detected in these corner radii because they are the highest stresses of the cups. Without lubrication, forming of DCO4 was possible without any failure. But using aluminum alloys, some crackings were identified, especially in case of AA5182. A strong thinning during deep drawing occurred in the highly stressed corner radii around about a drawing depth of 26 millimeters. In case of AA6014, an earlier cracking could be identified at a drawing depth to 80 millimeters. So the experiments told us that they are in accordance with the numerical simulations. However, without lubricants or coatings, there is a high chance to expect material failures and crackings while forming, especially for these aluminum alloys. So for this purpose, in the next step, we did some tribological tests in order to analyze the tribological performance of lubricated and unlubricated material compositions. For the characterization of the tribological behavior, the flat strip drawing test is commonly used to determine friction coefficients for deep drawing processes. Here in the upper left corner, you can see the basic principle of the applied test setup. The sheet metal, the blue line, which you can see here, is placed between two friction jaws. The lower jaw is moving upwards with applied normal, it's applied with a defined normal force. While the strip is drawing through the jaws, a distinct drawing velocity was set up, and the resulting friction force could be measured according to Coulomb's law of friction. At first, the reference strip drawing tests were carried out for deep drawing the steel TCO4 and two different aluminum alloys, the AA5182 and the AA6040, with a sheet thickness of 0.1 millimeter. The first experiments have been conducted under lubricated, the green ones, and dry conditions, these blue ones, to gain a basic knowledge of the impact of lubrication and deep drawing processes. You can see that the values of the friction coefficient vary between 0.03 and 0.59, depending on the lubrication and the sheet metal material. Without the use of lubrication, we gain much higher friction. This is no surprise, but we see at first that our testing works. Using lubricated sheets, the friction coefficient reach almost the same level for all material compositions. However, under dry conditions, the friction coefficient vary extremely, which might be explained by different strength of the workpiece and the different contact behavior of the tool material. In order to analyze the reason for the huge deviations between the friction coefficients, a surface characterization was performed after testing, which can be seen here in the lower pictures. And by using uncoated tools under dry conditions, adhesive wear locally appeared, which led to an increasing friction forces. These are these colored lines, which you can see as adhesive wear, which we can indicate it as adhesive wears. For this purpose, the ACH or DAC coatings were applied in the next step on the friction jaws to improve the tribological behavior. The test results can be seen here in the upper right corner. The tribological experiments with coated tools reveal that an improved friction coefficient was able to gain. For aluminum alloys, the friction coefficient could be significantly improved compared to those uncoated tools. The optical measurements after testing revealed that almost no changes at the planar contact tool area could be detected. So it is assumed that the high hardness of the coated tools improved the tribological behavior. In particular, it is assumed that the hard materials tend to be less prone to adhesion, since the overall amount of metallic bonding forces is significantly reduced at the blank die interface. So in the laboratory test, it was proven that the ACH and the TAC coatings reduce friction as well. However, the laboratory tests only investigate the tribological behavior for a lower number of forming operations. Therefore, the durability of the modification has to be investigated for a higher number of forming operations. The drawing of rectangular cups, which we had seen before, has been used to evaluate the tribological conditions. Is not suitable for this purpose because it's not capable to produce enough form parts. So this motivated us to develop a novel word test trick based on a high press speed. In this regard, you can see our tool, a follow-one composite tool, was used. The advantage of this kind of tool is that there are short cycle times and the high quantities can be achieved. The process basically consists of two steps: the stamping process and the following deep drawing. The cups, which you can see in the upper right corner, have a diameter around about have a diameter of 40 millimeter and a depth about 20 millimeter. The tool system thus enables us to dry forming of 100 cups per minute and is used to investigate the tribological behavior for lubricant free forming of drawing by using deep drawing tools. Yeah, to test the potential and the limits of the coatings, the aluminum AA51 was used at first as blank material. For the tools, uncoated, ACH coated, and the TAC coated tools have been used. The tool topography after forming can be seen here in the lower parts of the slide. After forming 10 strokes with an uncoated tool, significant wear occurred at the radii of the dies. By using the ACH coating, the dies also exhibited wear. However, the size and the shape of the worn area are clearly smaller compared to those in the uncoated tools. Yeah, with the TAC coated tools, there are no visible wear signs after 3,000 forming operations with the aluminum alloy AA51 82. So in this regard, the flat strip drawing test could be confirmed. The coatings reduce friction and wear, which in turn leads to an improved forming behavior of the forming tools. So yeah, further experiments have been performed with the DCO4 and AA6014. With all materials, a failure-free forming was possible. To evaluate the impact on the resulting blank roughness in the next step, optical measurements have been performed. The test results reveal that a significant improvement in surface quality, especially for the TAC coatings, which is the green one, was achieved. Furthermore, a homogeneous sheet thickness distribution for the TAC coatings was gained, whereas the ACH coatings led to a higher netting of the parts, which can be seen here, for example. The reasons for improved tribological behavior for the TAC coatings might be the extreme high hardness, like Professor Hagener told before, of the tool coating. Yeah, in particular, hard materials tend to be less prone to adhesion since the amount of metallic bonding forces is significantly reduced at these blank die interface. Furthermore, the TAC coatings reveal a good layer adhesion with a high abrasive wear resistance. Yeah, from research objective, the use of TAC coatings is more effective, although the application is quite more difficult. So the question now is, can the results be transferred to an industrial application? To find an answer, a new research project will be started at our institute. The main objective is to do an in-depth evaluation of TAC coatings under near industrial conditions. So the university moves more and more towards to the industrial applications. The methodological approach is as follows. In the first part, the tool workpiece contact has to be improved. For this purpose, different sheet materials, sheet textures, anti-corrosion protections are investigated under dry conditions. Furthermore, different stress strain conditions and material flows have to be implemented and tested to converge industry relevant components. In a following step, the coating quality is investigated. For this purpose, different part geometries or batch influences, for example, are characterized. In the last step, the long-term application behavior is analyzed to do a final assessment of the industrial benefit. The kickoff date for this research project starts on this Friday, and the whole research project will last about 2 years. The team basically consisting of 2 universities from Erlangen and Bayreuth, but also companies of all sizes like steel producers, lubricant producers, software companies, forming companies, big producers of cars are joining our project team. So we are eagerly awaiting the results of this nice team working on this interesting topic to all. Finally, Professor Hagener and I want to thank you for your attention, and now we are looking forward for your question.
So thanks a lot for sharing these insights. Now to everybody still out there and who is with us, please, if you have any questions, either write them down in the chat window or put them in the questions window. I see when they come in and I can pick them up right away. Meanwhile, surprise, surprise, I have some questions on my own. And one thing I was impressed of the carbon coating procedure that you showed, also the nice video you had. But from what I saw, this was more a small, let's say, small volume of parts that could be brought in. And when I remember correctly, Balsa's coating is usually coating cutting tools and stuff like that. So how do you see the application of this coating for real life, real size dies that are used in, let's say, blank production of car side panels?
Well, that's the question of scale up, which is always interesting, and I couldn't provide a direct answer. The nice thing is that we have figured out that TAC coatings are more suitable, which are not limited to these small areas if you take sufficient process time. However, of course, process time is a challenge there, definitely, if we are talking about side panels of cars, definitely. Stefan, do you have to add anything?
Yeah, I think it's also an objective of this new research project from another institute, just to improve the application behavior of these coatings.
But when I saw that right, that your coating provider, Oerlikon Balzers, is not part of that project. Right?
No, it's not part of it. It's just to show us how it works for.
Okay, understood. I see one question dealing with the ecological footprint. Did you do any analysis? How much oil, how much energy use, how much carbon footprint an application of your methodology would lead to? So how much better are we getting? How much are we saving? Is there anything you can give us what that means?
I'm not aware of these results. Also, I think they would be a bit early because you would need to see how this works in real world environments. From the lab, it's difficult. We see now that we can stand 3,000 parts. We do not know how many we can stand, and this is, of course, a vital impact, because if we have to change the tool, let's say every 3,200 parts, it is not comparable with what we could reach nowadays with lubricants, and would have a significant impact on the ecological footprint. So the question is correct and should be addressed at some point, but it should be addressed when we have come up with something that is really applicable and does stand a sufficient number of parts. Currently, we can say, yes, the process chain is shortened. We can be quicker because we don't have this. So from an economic point of view, it is interesting regarding process time. We do have some effects of not using certain lubricants and cleaning chemicals. However, all this might be nullified and not really effective in an ecological way if you come to energy consumption, if we need new tools too often. So we have to wait for these results to make a reliable and honest evaluation there. Currently, I can tell about all these nice things that we can observe and how wonderful it is, but it would not be honest to say it's wonderful because we don't have the final times that the tools stand.
Is there any website of this new research project where the interested audience can follow the results as they will be published?
There's no websites yet, but there is a website about the last research project, which lasted about 6 years. It's called SPP 1676. So if you Google it, you can find just the papers and the results of this 6 years ongoing research project we had before.
And of course, there will be a website regarding the new project on our institute's homepage as soon as the work starts, and this will be updated as publications occur. There will be on the website. And so if you are interested, you can follow on our homepage the development and the publications of the project. However, you don't have to be a prophet to know that it is very difficult to have publications within the first 6 months. You need results first, and then you need revision and so on. But it is there, and if you are really interested, of course, there's also the possibility to contact either Mr. Schirdewan as head of the sheet metal forming group, or to contact the researcher that will be aligned to the project once it is on the homepage.
Then I don't see any more questions. So thanks a lot to you, gentlemen, Professor Hagener, Mr. Schirdewan, for sharing this insight. Good luck for your future research. And let's hope that you will be able to cope with the scaling effects, and that we can see this nice technology in industrial application better sooner than later. And thanks for everybody from the audience who stayed with us. Have a great day. Have a great week. And I think today we can already say Merry Christmas and a good New Year. Goodbye.
Thank you very much. Goodbye.
Goodbye.